Okay, so let's simulate what you should do for your homework tasks. I mean, this is one of the things you can do, but as I explained in the document I sent you by Virtual Campus, you can employ many other ways to make this video, okay? In this case, we are asked to apply Thevenin's theorem on resistor RL. Here, this is the resistor. So we have to take a look to the circuit just to check what do we have. So we see here a 10 volt power source, 1 milliampere current source, and two resistors, two 1K resistors. So to apply the Thevenin's theorem over the resistor RL, this load resistor, what we have first to do is just remove the resistor. Okay, so if we remove the resistor, the circuit we have is the rest. Okay, now we have to do two things. One is calculate the Thevenin's resistance of your circuit, of your equivalent circuit, and the voltage of the Thevenin's voltage of your circuit. Okay, we can do it in just different, let's say, options. We can start by resistance and then later calculate the voltage, or the other way around. Okay, it doesn't matter. So I will start with the Thevenin's resistance because it's usually easier, and to do that we just have to kill all power sources, meaning that we have to short circuit the voltage source and we have to open the circuit in the current source and leave the rest of the elements in the circuit. Of course, this load resistor is not connected here. Okay, let me put it in red. This resistor is not connected. Okay, so the circuit is open between A and B. So if you see, since this part is open, the resistance between points A and B is 1K in series. Let me put it in another color. 1K in series with another 1K resistor. So finally, the Thevenin's resistance is 2K. Okay? 2K. Now, regarding the Thevenin's voltage, what we have to do just is solve this circuit. Okay? So to solve this circuit, we can apply the Kirchhoff voltage laws, taking into account that there is no voltage drop in this 1K resistor. Okay? This branch has no current. So if there is no current, there is no voltage drop in the resistance. Okay? So the only thing we have to do is solve this loop or this network that we have here in pink. We apply the Kirchhoff voltage law. Just the 10 volts have to be split between the voltage across the current source and the voltage between the points A and B. The points A and B, okay, since they are these points here, are the same and as these other ones. Okay, so the voltage in this 1K resistor that I'm pointing out now is the same voltage as between the points A and B. So solving this equation and knowing that the current through the resistor is 1 milliamp because it's forced by this current source here, the Thevenin's voltage, which is the voltage between A and B, is 1 volt. Okay, 1 volt. If we have 1 volt between A and B, then in the current source, it's not mandatory to calculate it, but we can say that in the current source we will have 9 volts, the difference between 10 and 1. So the final Thevenin's equivalent circuit between points A and B is this one. Okay, we have here Thevenin's voltage, 1 volt, Thevenin's resistance, 2K, and the load resistance. I have prepared a simulation here in LTSpice just for you to see that both circuits, the top, that is the original one, and the bottom one, that is the Thevenin's equivalent, are the same, or at least behave the same. So we are going to simulate here, put the windows vertically. Okay, so the first thing we are going to see is the current through the load resistor. In this case, I put a 100 ohms load resistor. So as you can see, the current is more or less 0.5 milliamps, something like that. And if we check the current through the load resistor in the Thevenin's equivalent, we will see that both lines are overimposed. Okay, one is over the other. We can also put another signals, but an important thing that we have to check is the power handled by this resistor. Okay, the resistor on the top and the resistor on the bottom, you can see that they have the same amount of power. That is very small. We can make a zoom here just to see that we are handling microwatts. Okay, that is almost nothing. So that's it. Thank you.